Alright, in today's lesson number 3, we're going to talk about molar concentration. Now, what is molar concentration? Molar concentration can be calculated as long as we have stoichiometric ratios to help us solve. So we're going to apply what we learned in mole concept with concentration. And we're going to use molar ratio to help us solve now between various species using concentration. Now remember, concentration, as we recall, was this. So concentration in chemistry is equal to the number of moles over volume. Now what that means is C is equal to N over V. Now we could rearrange this equation by multiplying both sides by V to solve for N, where N, the number of moles, is equal to C times V. Now this is going to be a very powerful equation that we're going to use quite often in this class because this is going to allow us to solve for what we call unknown concentrations in a bit. Now here's a little note though. When given volume, do not assume STP unless stated otherwise. So in this lesson, we're not going to use STP unless it's stated otherwise, okay? Just like whenever you're dealing with any other previous questions, if STP is not stated, you cannot use STP to help you solve. Alright? So let's try our first example. Barium hydroxide, BaOH2, has a mass of 0.5000 grams. What volume of HCl, that is 0.250 molarity, is going to be needed to neutralize this barium hydroxide? So we're going to use our stoichiometric ratio, our mole ratio, to help us solve. So currently, we're given two values. We're given the mass of barium hydroxide, and we're given the volume of HCl. So what do we need to do? Well, we need to first of all know that our concentration can always be used as a conversion factor because it's made up of two or more units. In this case, it's a derived quantity. So what do we have? We have 0.500 grams of barium hydroxide. And we need to get this to moles of barium hydroxide. So we gotta use the molar mass. Now what is the molar mass of barium hydroxide? Well, if we look at our periodic table, we will find that the moles of barium hydroxide, or the molar mass of barium hydroxide, is 137.3 plus 2 hydrogens, which is 2, plus 2 times 16 oxygen, which is 32, we get 171.3. So 1 mole of barium hydroxide is equal to 171.3 grams. So our grams will cancel out. Now our next step is now to solve for our moles of hydrochloric acid, because that's what we're going to get to. So looking at this, our molar ratio is 1 mole of barium hydroxide reacts with 2 moles of hydrochloric acid. So we want our 2 moles of HCl on top, and our 1 mole of barium hydroxide on the bottom, because thus our moles of barium hydroxide will cancel out. Our last step is to use our concentration of HCl to help us solve for volume HCl. Now we know that this value is 0.250 moles per liter. That's what concentration is. It's moles per volume. Now in this case, where should our moles go? Our moles should go on the bottom. So we have 1 liter over 0.250 moles of HCl. And thus, now our moles of HCl will cancel out, and we're left with just the volume in liters as our only unit. So what I gotta do is now I plug all these values into my calculator. 0.5 divided by 171.3 times 2 divided by 0.25. And I get 0.0234 liters. And if I were to write this in milliliters, it will be 22.23 0.4 milliliters. Either of these answers will give you the correct value. Now, what we have here is an example of using molar concentration to help us solve for our unknown volume in this case. So this is one example of what we use molar concentration to help us solve when we have molar ratio. So let's look at our next question. In this case, you're looking for the volume of CO2. And this time it is at STP, because CO2 in this case is a gas. So because it's stated at STP, you can use 22.7 liters per mole. You can use this now. So that's one example of this. Okay. Now, what we have next is we have that this is produced if 2.5 liters of 0.150 molarity HCl reacts. Okay, so that means you have HCl, hydrochloric acid, will react with calcium carbonate. Well, calcium carbonate is basic, and when it reacts, it doesn't really neutralize the same way we usually have a neutralization reaction. It instead produces CO2 plus H2O, and the salt is always made up of the metal of calcium carbonate and the non-metal of the acid. In this case, it will form CaCl2. Now, if I balance this reaction, I will get 2 HCl right there to help balance out the rest of the reaction. So this is an example of what we call a hydrochloric acid reacting with a carbonate. All right. Now, what we got to do next is what we got to solve for is how do we solve for what volume of CO2 will be produced. Well, we first of all want to find what is the moles of HCl, because if we find the moles of HCl, we can now cross the mole ratio to get to CO2. So we go 2.5 liters times. This concentration can be used as a conversion factor where it's 0.150 moles per liter of HCl. Now I'm in moles of HCl. What can I solve for? I can now cross the mole bridge to help me solve for the for CO2. So the mole ratio here is 1 mole of CO2 over 2 moles of HCl. So now liters cancel out, moles of HCl cancel out. I'm now in moles of CO2. My last step is now to try to solve for volume of CO2, which I could use STP, 22.7 liters per 1 mole. And now moles of CO2 cancel out. So I'm just left with the volume of CO2. If I plug all these values in my calculator, what do I get? Well, I have 2.5 times 0.15 divided by 2 times 22.7. And I will get two sig figs, because the least number of sig figs in this case is 2. I will get 4.3 liters of CO2 gas will be produced. So this is an example of, in this case, how we solve for volume when it's dealing with STP. Now what we're going to move on to is what we call a titration. It's when we want to solve for an unknown concentration of something. Alright, so what is a titration? It's to find the concentration, so in square brackets, writing concentration of an unknown. So, but this substance that we have unknown has a known volume. So it has a known volume. It just doesn't have a known concentration. And usually we perform with an acid base. And we use a tool called burette. So we use a burette and flask to perform. Now, what is a burette? A burette is a specialized tool. So if I open up this right here, you can see that a burette is a tool in which it's a glass rod that has number markings like a graduate cylinder. Now, the number markings go backwards. They go and they count from top to bottom. Now, why is it count from top to bottom? Because it's tracking not how much volume you have, but how much volume you've used. So if you start at 0 and you used up to, let's say for example, 21 milliliter, what that means is you now have a final volume of 21, an initial volume of 0. To find the volume used, it's always final minus initial. 21 minus 0 will be 21. Likewise, if your initial was 4 and your final is 20, 20 minus 4 is 16. So this is why a burette is used with the number system counting backwards. Now, how does a titration work? Well, a titration works in this case. You have a flask. The flask has a known volume, but an unknown concentration. It's what you're trying to find the concentration of. Okay, so it's what you're trying to solve to find this concentration of the substance. You have a burette, which has a known concentration, and eventually you're going to add into flask. And you also have an indicator. And an indicator is added into the flask, in which it will change color at a certain pH. And usually you want that change to occur at what we call the equivalence point. So we're going to use something called the equivalence point to help us find our unknown concentration. So what we do, we're going to, so if I copy this picture in to here, you're going to be able to see that, if I copy this picture here, there we go, you're going to see that a titration works like this. You're going to have, in this case, as you can see, you're going to have some unknown concentration in this flask with an indicator. You're going to have some known concentration in the burette. And you're going to slowly start to add your substance in the burette into the flask. Eventually, once you add it to a certain point, the indicator will change color, and you've now reached what we call the equivalence point, or a stoichiometric point. Now, what is this stoichiometric point? Now, if you're still having issues with what this looks like, you could YouTube a video of how a titration works, and that usually gives you a lot more detail. So what is the equivalence point? The equivalence point is where the moles of your known substance and the moles of unknown substance matches their mole ratio. So what that means is you will reach the equivalence point when that solution changes color because of the indicator. It will happen when the mole ratio is met, and that is why you need a balanced equation. So let's flip the page of your notes and let's look at an example of this. So an example of this would be, for example, if you have barium hydroxide and it reacts with hydrochloric acid, will form barium chloride and water. So in this case, the equivalence point will be met when your acid and base matches a 2-to-1 ratio. So if I were to write this down, equivalence point is when you have 2 times the mole of HCl to barium hydroxide. That means you have twice the amount of moles of hydrochloric acid in that flask as you do barium hydroxide. So here's a big note though. Equivalence point is when the mole ratio is met, not their concentration. And we're going to look at that with a few examples. So let's try this first example of how this works. For the reaction, sulfuric acid reacting with sodium hydroxide, you're going to form salt and water. If an unknown concentration, that means your H2SO4 is in the flask, and we add a 0.800 moles of NaOH. So that means that is something that we know for it to reach equivalence point how many moles of H2SO4 is in the flask. So if I look at this example, I have 0.800 moles of NaOH. How do you find how many moles of H2SO4 there are? You cross the mole ratio. You cross the mole bridge. In this case, it's 1 mole of H2SO4 to 2 moles of NaOH. And thus, your moles of NaOH will cancel out. And thus, you're going to be left with the moles of H2SO4, which is going to be 0.400 moles of H2SO4. So that means when you have, so if we look at this previous picture here, when you have in this flask at equivalence point, when you have 0.400 sulfuric acid and 0.800 NaOH in this flask, you would have reached equivalence point. That is when the solution will change color using indicator used. So that is what we mean by equivalence point, when these moles match their ratio. As you can see, you should expect twice the amount of moles of NaOH versus H2SO4. So let's use this idea now of finding concentration. If an unknown concentration of this same reaction, so in this case 0.025 liters of NaOH is in a flask, and we add 0.500 moles of H2SO4, what is the concentration of NaOH in the flask? Well, this is our volume. We know that concentration is equal to moles over volume. We can find concentration if we have moles and if we have volume. We have our volume. It's 0.025 liters. We just don't have the moles. So we could solve for the moles by solving 0.500 moles of H2SO4, cross the mole bridge to get to NaOH, which is 2 moles of NaOH over 1 mole of H2SO4. And thus we could solve that our moles of NaOH is 1.00 moles of NaOH. So now what we want to do is we want to now take our moles of NaOH and divide by our volume, because C is equal to N over V. 1.00 moles divided by 0.025 liters. If I punch this in my calculator, 1 divided by 0.025 is going to give you 40. You're going to get 40 molarity. Now, if you were to write this as correct sig figs, currently this is not correct sig figs. You want to make sure that your answer has 2 sig figs, because 2 is the lowest number here. So how do you turn 40 into 2 sig figs? You could write it in scientific notation. It becomes 4.0 times 10 to the 1 molarity. So that is a way of trying to solve for the concentration of an unknown. What we're going to move into is, what does an actual titration look like if we were to solve it? So let's look at example number 4. In example number 4, it takes 21.55 milliliters of NaOH at 0.500 molarity to titrate 25 milliliters of H2SO4. So that means our H2SO4 is unknown. So if I look at my previous picture, you have H2SO4 in this flask, you have NaOH in this burette, and you're going to add 21.55 milliliters of this NaOH in the burette into this flask that already has 25 milliliters of sulfuric acid, H2SO4. And only after you added 21.55 milliliters of NaOH does this flask reach equivalence point. Only when that's when it reaches its equivalence point, so you can use your mole ratio to solve. So what do I do? Well, I gotta find how many moles of NaOH I have, because if I find how many moles of NaOH I have, I can now find how many moles of H2SO4 I have. So you might remember that if you're given volume, if you're given concentration, you could always find moles, because moles is equal to concentration times volume. So in this case, your concentration of your NaOH is 0.500 molarity, your volume is 21.55 milliliter. So in this case, you have 21.55 milliliters. But concentration is moles over liters. So we gotta convert this milliliters into liters. So we have 1 liter over 1,000 milliliters to solve initially. So our milliliters cancels out. Our next step is now to get to our moles of NaOH using our concentration, which is 0.500 moles of NaOH over 1 liter. And thus now our liters will cancel each other out. Now I could cross the mole bridge. My mole ratio is 2 moles of NaOH and 1 mole of H2SO4. So 1 mole of H2SO4 over 2 moles of NaOH. Now how do we find concentration? What is molarity? Well, that means we have now just solved for our moles of H2SO4. Our last step means that we divide by our volume of H2SO4. Now how do you do that? Well, you could actually expand this calculation some more by multiplying by 1 over this value in liters. Now 25 milliliters is the same as 0.025 liters. If you multiply by 1 over 0.025 liters, you actually just solve for moles over liters. You could also, after this equation hit equal, solve for where we have for moles of H2SO4 and then divide it by 0.025 liters. That could also work as well. So what you have here is now, you punch this in your calculator. 21.55 divided by 1,000 to get to liters, times by 0.5 divided by 2 divided by 0.025. And you're going to get 0.2155. So 0.0 or 0.2155 is your concentration. 0.2155 molarity. Now you want to make sure that this is the correct number of sig figs, which means that you got to make sure you round to the least number of sig figs. In this case, that number is 3. So if you round this to 3 sig figs, which should round to the 3rd decimal place, this is now rule 5. You want to always round this number to the even number. In this case, you will get 0.216 molarity. Now if we look at the last example, again, you could pause this video anytime and try it out on your own. So let's look at this one now. What volume of 0.450 molarity KOH is required to react with 150 milliliters of 0.300 molarity of H3PO4? So here is your reaction. So what do you have here? You have a concentration You have a volume, you have another concentration that applies that volume. You always want to get to moles. So which one of these numbers can get to moles? Well, if you have your volume and you have your concentration, you could always get to moles. So remember, number of moles is always concentration times volume in this case, has to be in liters. So what do? Well, you convert this volume into liters, which should be 0.150 liters. So you have 0.150 liters times by your concentration, which is 0.300 moles of H3PO4 over 1 liter. That should cancel your liters, you're now in moles, of H3PO4, cross your mole bridge of 2 moles of KOH over 1 mole of H3PO4, phosphoric acid. Your moles of phosphoric acid cancels out, and now you're in moles of KOH. But you want to find volume. Hey, you have the concentration of KOH. You could find volume by using this as a conversion factor, because this number is 0.450 moles per liter, which means that if you put the reciprocal of it, it'll be 1 liter over 0.450 moles of KOH. And that should cancel out your moles of KOH, and thus you're left with liter. So once you punch this on your calculator, you now can find what the volume of KOH will be. Well, 0.15 times 0.3 times 2 divided by 0.45, and you're going to get 0.2 liters. Now if this is correct number sig figs, you would see that you'll need 3 sig figs, so you're going to get 0.200 liters or 200 milliliters, which you need to write in correct sig figs, 2.00 times 10 to the power of 2 milliliters. So that is how you solve using titration. Now, what are some things we should remember so we don't make mistakes? The biggest thing we need to know is equivalence point. Equivalence point is when the mole ratio is met, not concentration. As long as you know once equivalence point met, you could use the mole ratio to help you solve. It just means doing your standard stoichiometric calculations. Now your homework for this section is going to be page 131, number 17 to 25 odds. As always, make sure you stay safe and healthy, and I'll see you soon.